Greetings, students. Mr. back with you again today. We're going to continue on. The last completed was a short one over Q, action quotient, and its relationship to K, the equilibrium. I said that accompanying assignment, which was equilibrium assignment, was so we're continuing on today. Continue on with our next lesson over Chatier's principle, which honestly probably one of the important principles. The most used out in industry. So today, didn't mean to do that. Sorry about that. There we go. So, just picking up right where we left off with Q versus K. So, in this process, from hydrogen and nitrogen gases, the German chemist Fritz Haber sought the factors that might be varied to increase the yield of NH3. Let me go back on Fritz Haber. He might be a guy, if you're interested in wanting to Google or look up on the internet, he is quite famous. He won the Nobel Prize in 1918 in chemistry for his work with ammonia. I recall that 19 also interestingly enough, end of World War I. Fritz Haber played an extremely important role for the German government in World War I. Ammonia has several important uses. The main one, I should say, is in that ammonia is the main ingredient in fertilizer. Without the ability to mass produce ammonia, there is no way a crop yield would be what they the to mass on a very large scale that led us out of where lots of very farms whereby farmers just grew crops for basic themselves, their own family, and local community. Now to a level of where crop yields are so much higher that even with few farms, we are able to not only grains to feed communities, but to export billions and billions of dollars of grain. Without the ability to manage ammonia or fertilizer, would not have happened. Another important use of ammonia is in the production of nitric acid, which is used in the production of explosives. So it is in that regard Haber, played an important role in the German government during World War I. In fact, not only in the production of explosives, but he was also able to synthesize a process government, chlorine gas, which is a common name of mustard gas. And if you guys know or remember anything about World War I, the Germans introduced mustard gas as a chemical during that war. World War I was called the war, where the went on in the trenches. One side dug a trench here, another side dug a trench here, and they would fire ammunition back and forth. Mustard gas is very, very like I said, it's chlorine gas, and if you inhale it, basically what happens is the moisture or water in your lungs and airways reacts with that chlorine gas to produce hydrogen, which is extremely corrosive. It will burn the lines of your trachea and your lungs, and in fact, will produce acid, suffocate, or you will drown. Very and horrible way to die, and Fritz Haber was very much involved with that. A little historical side at the top. In regards to ammonia, like I said, out him where we are today to agriculture. So anyway, we back in the very beginning of this unit when we talked about KP, actually calculated the KP for production of ammonia, nitrogen, and hydrogen gases, and in fact that value of KP is very, very small. I think it's somewhere on the line of 4 times 10 to the minus third. All right, that's a pretty small number. So what that means is equilibrium quantity of product, which is ammonia, versus the quantity of the reactants, nitrogen and hydrogen, is very small. So as the equilibrium is set up, it's not very conducive to producing large amounts of ammonia, which obviously we need to do. However, vary the temperature and total pressure of the system, remember it's a closed system, based on a principle put forward by the French chemist Henri Lavoisier. If a system at equilibrium is disturbed, a change in pressure of one of the components, then the system will shift its equilibrium so as to counteract the effect of the disturbance. This is known as Le Chatelier's principle. Le Chatelier's principle is any equal process our system, all right, and it forms very many equilibrium reactions that are key to remaining alive. For instance, water content. So we talked about osmosis moves in and out of the cells because the cells have to be hydrated. Remember, our bodies are about 70% water. Cells have to be hydrated to a proper level in order for certain bioprocesses within our body to work correctly. And so basically what that says is if our bodies are stressed by they do not have enough to become dehydrated, the natural reaction that gets and so and that's an equilibrium process involving Le Chatelier's principle. The body is stressed by a lack of water. The brain tells you drink. All right. Another one, temperature. You know, our bodies are set to run properly around 30 degrees Celsius, 98.6 Fahrenheit. When our temperature goes up, if we get all right, then the stress to the body, our body is hot. Our body gets too hot, you know, it starts pushing 100, 405 degrees Fahrenheit. It's going to cause some serious problems. All right, and so react to an increased temperature. It begins to shiver, which helps release heat from the body. It increases the surface area. You get boost surface area of skin more rapidly and be lost from the because remember blows from warmer, cooler environments, and so that's another natural biochemical process involving this principle. So let's look at changes in product or reactant concentration. The shift will be in the direction that minimizes and reduces the effect of stress. All right. So if more is added, whether it be in our product, the reaction will shift to consume that reaction is added. Then the reaction is going to shift to the right where the products are, make more additional reaction. So if more of a substance is added, the reaction will shift to that's basically what that means is the net effect of that is if to the opposite side. Right? If you add reactant, which is on the left, it will shift to the right to form more product. If you add more product, which is on the right, it will shift to the left to make more reactant. All right. Removal of a substance result in emission shift more substance. All right. So the same thing. So if you take the stress is now there's not enough of it, so shift in order to make more will then negate the effect, decrease the effect of the stress of a substance then shifting to reduction of that substance, which then means and the effect of that is it will shift to the same side. And we're going to look at some specific better. Number two, for changes affecting volume and the resulting pressure change. Okay, this is how Boyle's law. Remember, volume and pressure are inversely proportional. If a system's at equilibrium and its volume is decreased, in other words, it's taken from one container and put into a smaller one, then the pressure increases. Boyle's law tells us that. And according to Le Chat system, by shifting equilibrium, reduce. We put a equilibrium reaction mixture in a smaller container, whereby the volume is smaller, pressure in that container increases. So stress is high. What we want to do is reduce. The pressure can be reduced by lowering the number of moles of gas. All right, lowering the number of moles of gas. So in the direction in which there are a fewer number of moles, check about that. Here, if its volume increases, if its volume is decreased, then its total pressure increases, which means the stress is the pressure is too high. All right, and so the reaction is in order to reduce the pressure. All right. So if the pressure is too high, all right, then it's going to shift. It's going to shift to the side with less moles, whichever side that may be. That would then decrease the pressure. That's Avogadro's law. Remember, moles and pressure are directly. If you lower the moles, the pressure is going to go down. And if the pressure is too high, that's what you want to do. All right. All right. So as we move on to the next page, so conversely, if the volume is increased, so if we take our reaction mixture and put it in a larger container, of course, then by Boyle's law, the pressure will decrease. And so now the stress is that our pressure is too low. And so thus, the equilibrium is going to shift in the direction that will increase the pressure. All right. So the reaction will shift in the direction in which now there are the greater number of moles. Again, Avogadro's law, more moles, more pressure. So if the pressure goes down, then the equilibrium is going to shift to the side with more moles. Okay, more moles. So because that will increase the pressure. Now, for changes in temp. Recall that some reactions produce heat. Those are exothermic reactions where delta H or enthalpy is negative. And others absorb heat where heat is a reactant, heat is absorbed, and so delta H is positive. Le Chatelier's principle states that when the temperature of a system is increased, the equilibrium will shift in the direction that absorbs the additional heat. In other words, to get rid of it. In an endothermic reaction, all right, increasing the temp will shift the reaction to the right. So think about that. An endothermic reaction, the heat is on the left side of the reaction. It's on the reactant side. If we increase the heat, and so now that side of the reaction is too hot, we want to use that heat up. And so it will shift to the other side, because if you shift it to the left, it's just going to produce more reactants and thus more heat as well. All right. So adding heat then, and of course then for an exothermic reaction where heat is on the right, if we add more heat, we're going to shift it to the opposite side, to the left. So shift to opposite side. to remove heat. Okay. In an exothermic reaction, increasing the temperature, as I said a minute ago, will shift the reaction to the left for the same reason. Lowering the temp or cooling it down will have the opposite effect. All right. So if we remove heat, so now the stress of the reaction is it's too cold. So now we want to make more heat in order to warm it back up. And so now it's going to shift to the same side in order to add heat. Okay, so that involves temperature. All right, let me advance this up. We'll now look at the effect of adding a catalyst. So we talked about catalysts in regards to lowering activation energy back in Unit 12.1. So adding a catalyst lowers the barrier between the reactants and products. It lowers the activation energy. Remember, we dealt with the Arrhenius equation with this in Unit 12.1. But it does not change the composition of the reaction equilibrium mixture. All right. So basically, there's no change. All that happens when you add a catalyst is that equilibrium is achieved quicker. The forward reaction is moving faster, the reverse reaction is moving faster, and so equilibrium is achieved faster. But it does not affect the composition of the reaction mixture. Right? So it just increases the speed at which equilibrium produced. But since the reaction mixture's numbers haven't changed, then that ratio of products to reactants has not changed either, and so K remains unchanged. Okay? I want to add one more thing. We're going to add a number 5, all right? Adding a noble gas. To a mixture of gases. Okay? So this involves reactions that involve gases only. In other words, all the reactants and products are gases. All right? What the effect of that is there isn't one. No change. All right? So let me explain that. Because it would seem like, as from what we talked about earlier, now if we're adding another gas, the pressure's going up, right? Which means the pressure's too high, that's the stress, so we want to decrease the pressure, et cetera, et cetera. That is if you add a gaseous component of the mixture. In other words, adding a gaseous reactant or product. When you add a noble gas, think about the noble gases. They're inert, they're unreactive. Right? They're not going to, the other gases in the reaction mixture are not going to react with the noble gas. All right? That's the important thing. So other gases in the reaction mixture do not react with the noble gas. All right? They don't react with it. So their partial pressures remain unchanged. On both sides of the reaction. So think about that. The overall pressure in the container has gone up since you've added a noble gas. But since the reactants and product gases are not reacting with it, then their pressures remain unchanged. And thus the ratio of the product pressures to the reactant pressures, or Kp, hasn't changed either. All right? So K remains the same. So adding a noble gas to a reaction mixture of gases does not affect K. Right? And so there will be no shift in equilibrium. All right, so let's look at an example and see and summarize then how Le Chatelier's principle works here. Okay? All right, so consider the following equation for which delta H equals negative 197.8 kilojoules. Okay, so that tells us this reaction is exothermic, meaning that that heat is a product. So let's just go ahead and take care of that right now. Plus 197.8 kilojoules. All right. How will each of the following disturbances or stresses affect the equilibrium mixture of the three gases in this reaction? So, letter A, O2 is added to the system. All right, so basically what you want to ask yourself is, okay, so how's that stressing the reaction? Well, the stress is now there's too much O2. There's too much O2. So to relieve that stress, what do we want to do? Well, we want to use it up. So think about that now. In what direction would the reaction shift in order to do that? Well, let's look at it. What you got to remember here is in an equilibrium reaction, you have two reactions going on simultaneously: the forward reaction and the reverse. So you got to look at it both ways. So if we add too much O2 and the stress is add more O2, I should say, and the stress is there's too much, what's going to happen? Well, if we shift to the left, we're going to use these up to make more SO3. Okay, that sounds good. If we shift to the right, we're going to use this up to make more of these. Well, if the stress is there's too much O2, do we want to make more O2? No, we don't. We want to get rid of it. And so the reaction is going to shift to the right in order to use up this additional O2 to make more SO3. So it's going to shift to the right. Okay? The reaction mixture is heated. Stress is now it's too hot. It's like when you have a fever. What's your body want to do? It wants to get rid of the extra heat. All right? We talked about that earlier. So to relieve the stress, we want to use up the heat. All right. So let's take a look at the reaction. If we go to the right and heat, this is an exothermic reaction. If we shift to the right, we're going to make more heat. The reaction's already too hot. You want to make more heat? No, I don't think so. All right. But if we shift to the left, we use up this heat and this SO3 to make more of these. That's what we want to do. So we want to shift left. Okay. The volume of the reaction is doubled. So we take the reaction mixture and we put it in a larger container. Remember, if the volume goes up, the pressure goes down. It's Boyle's law. Right? The pressure is going to go down when that happens. So the stress is the pressure is too low. So to relieve the stress, we want to increase the pressure. Here's where you got to look at Avogadro's law, all right, where number of moles and pressure are directly proportional. So if we look back up at the reaction, we have on the reactant side 2 moles of SO2 and a mole of O2, which is 3 moles total. And on the product side, we have 2 moles of SO3, so 2 moles total. If we want to increase the pressure, we want to go to the side with more moles. In this particular reaction, that is the left side, all right? So we want to shift left. Shifting to the left will produce more of these, more moles, pressure goes up, okay? A catalyst is added to the mixture. Well, we just talked about this a little bit ago. There is no effect or no shift, all right? Just equilibrium is achieved faster. It's the only thing it does. Okay. Total. Next one. The total pressure of the system is increased by adding a noble gas such as helium. All right. We just talked about this too. Adding a noble gas to a mixture of gases, although it increases the total pressure in the flask, it does not increase or decrease the pressures of these 3 substances here. All right. because none of these three will react with the helium or whatever noble gas it is. And so um, their pressures remain unchanged, and so the ratio of their pressures remains unchanged as well. All right? So no effect there. All right? The pressure of other gases remains the same. And so there is no change in equilibrium. Next one, SO3 is removed. All right, removed. All right, so the stress now is there's not enough SO3. So to relieve that stress, what do? Well, if your brain tells you your cells don't have enough water, you're getting dehydrated, what's your brain tell you to do? It tells you to drink more water. All right, same thing here. The stress is there's not enough SO3. We relieve that stress by making more. Which direction will do that? Well, if we go to the right, we make more SO3. If we go to the left, we use up SO3 to make these. We don't want to do that, all right? So it's going to shift to the right. Shift to the right, okay? And I'm going to advance the screen here. Letter G, the reaction mixture is cool. Okay? So stress now is it's too cold. All right? So to relieve that stress, we want to make more heat. Right, make more heat. Well, here again, this is an exothermic reaction where heat is on the right side. We want to make more heat, then we're going to shift that thing to the right, because going left to right, we're going to make not only more SO3, but we're also going to produce more heat. That'll heat the reaction back up. So it's going to shift right. Okay. If you were asked how to maximize the amount of sulfur trioxide produced, all right, then what suggestions would you make? So we want to maximize the amount of SO3 produced. SO3 is on the product side. So basically what it's asking here is what can we do that will cause this reaction to shift to the right, all right? Do everything that will shift reaction to the right, all right? So as we look back at our list that we just looked at, and see what we could do to shift this reaction to the right to make more SO3. Well, the very first one was add O2. We add more reactant shifts right to make more product and use that reactant up. Now, I didn't mention SO2. That was in one of our questions, but we could certainly do that too. So let's go ahead and put that in. We could add more SO2. The other reactant, the same thing's going to happen. All right, it's going to shift right to use it up. And in doing so, we'll make more product. The one we just looked at here, letter F, we could remove SO3. If we remove the product, then the reaction's going to, the stress is there's not enough of it. The reaction's going to shift to make more. So it's going to shift right. This one right here, we could lower the temp. The reaction's too cold since it's exothermic. Now, if it was an endothermic reaction, it'd be the opposite. But since this is exothermic, if we lower the temp and stress the reaction in such a way that it's too cold, it's going to shift to the right in order to make more heat, okay? Which is what we want to shift right. And then the last thing we could do is put the reaction mixture in a smaller container, right? So run the reaction in a smaller container as compared to a larger one, all right? Which then will, of course, increase the pressure. If the stress is the pressure's too high, it's going to shift, according to Avogadro's law, to the side that has fewer moles, which in this case is the product side, the SO3 side, and that is what we want. So summarizing this right here is exactly what Fritz Haber was looking at in trying to maximize the amount of ammonia made in the reaction. Hydrogen and nitrogen react to make ammonia. Like I said early on in the lesson, that K was very small. So under standard conditions, all right, you don't get much product. So he had to stress the reaction in ways that would force the reaction to shift to the right so that we could make ammonia in mass quantities. Again, Le Chatelier's principle is so key to not only industry, whereby we can make mass quantities of substances that normally standard conditions would say, with a K value, would say that we couldn't. And it's also vitally important to the equilibrium reactions within our bodies, the biochemical ones that keep us healthy and alive. So that is Le Chatelier's principle. So after this lesson, you should be able to do, I believe it is equilibrium number 7, Le Chatelier's principle. And then we will move on next to our next lesson. We're going to start talking about another K, the K involved with acids, and then following that, bases. So that is the end of today's lesson. Until next time, this is Mr. Keister signing off. Everybody take care, stay safe, keep working, be diligent. We're getting close to the end. So keep after it, guys. Take care, and I'll see you next time. So long.